In this lesson, we're looking at the process of integration by partial fractions. So obviously the whole idea is at the start, we want to go through that process of partial fractions, break it into the two individual fractions or more. And after we have done that, we can integrate the individual parts. So I'll go through a couple of examples so you can see the process in full. In this first example, where we have two linear denominators. So before we worry about the integration, we're just going to consider the fraction in itself. So 3x plus 5 on x take 1, x plus 3 will be equal to, because they're both linear, a over x take 1 and b over x plus 3. Once we've done that, we can say 3x plus 5 is equal to a multiplied by x plus 3 and b multiplied by x take 1. Now both sides will have common denominators, so we can ignore them. And now we can look at using that cover and check method. So when x is equal to 1, we've got 3 plus 5 is equal to 4a and 0b. So 8 is equal to 4a, and therefore a is equal to 2. When x is equal to negative 3, so that's where we get our second 0 from, we've got 3 by negative 3, which is negative 9 plus 5, and we've got 0a and negative 4b. So we have negative 4 is equal to negative 4b, and therefore b is equal to 1. So now we can say that the integral of 3x plus 5 over x take 1 and x plus 3 is equivalent to the two individual integrals
is equal to the integral of a on x take 1, which will be the integral of 2 on x take 1 with respect to x, and b on x plus 3, which will be 1 on x plus 3 with respect to x. So now we can integrate each of these. This will be 2 integral of 1 on x take 1, which makes the numerator the derivative of the denominator. And the second one we can integrate straight away because it's already the derivative of the denominator. That will be ln x plus 3 plus c. So now we've got 2 ln absolute value of x take 1 ln x plus 3 plus c. And using our log laws, we can say this is ln. And so we have ln x take 1 squared and ln x plus 3 plus c. So when we combine these, we get ln x take 1 squared x plus 3 plus c.
And there it is, there's our solution. So first of all, that process of partial fractions, once we get our partial fractions, we put them back into the integral, and then it's just a matter of doing those simpler integrals than the original. Okay, so example 2, we've got integral of 3x plus 1 over x plus 2 squared. So we're going to consider just a fraction. 3x plus 1 over x plus 2 squared is equivalent to a on x plus 2, because this is repeated, plus b on x plus 2 squared. Now all we need to do is multiply the first one, a, by x plus 2, and we've got a common denominator here. So when x is equal to negative 2, we get negative 6 plus 1 and 0a and b. So b is equal to negative 5. Now if we need to find a value for a, we can choose any other value. So let's say when x is equal to 0. And so now we've got 1 is equal to 2a plus b. b we already know is negative 5, so we've got 1 is equal to 2a take 5. 6 is equal to 2a, and therefore a is equal to 3. So now we can say that the integral of 3x plus 1 on x plus 2 squared dx is equivalent to 3 over x plus 2 integral of, with respect to x, and negative 5 over x plus 2 squared with respect to x. So two different integral approaches here. This becomes 3 integral of 1 on x plus 2 dot dx. So this is a special quotient, nice and easy. The second one, we can move this up and it becomes negative 5 integral x plus 2 to the negative 2 with respect to x. So we've got 3 ln x plus 2. We have negative 5. Now, when we find the integral, we add 1 to the power, divide by the new power for this one, and also divide by the derivative of the inside. So this becomes x plus 2 to the negative 1 over negative 1 multiplied by 1 plus c. So we've got 3 ln x plus 2. We have plus 5 x plus 2 to the negative 1 plus c. And power of negative 1 means we can move that back to the denominator. So plus 5 over x plus 2 plus c. There we have it. There's our integral. A little bit more complex, that one, but not much. Still the same process. Okay, now this one will be familiar. We have to start this by looking at the polynomial division. So we need to first look at x to the power of 5, and we'll put our plus 2 over here, and we'll divide him by x squared take 1. Now the reason we're doing the polynomial division is because we have an improper fraction, that is that the power of the leading term is greater than the power of the leading term on the bottom, so we've got power of 5 and power of 2. If that's ever greater or the same, we have to go through this process. So x to the power of 5 divided by x squared is x cubed. We'll subtract the product of x cubed and x squared take 1, which is x to the power of 5 take x cubed. So we'll throw in up here plus 0x cubed because there was nothing there. We end up with take away a negative x cubed, which is a positive x cubed. This is our new leading term. X cubed divided by x squared is x, and now we'll subtract the product of x and x squared take 1, which is x cubed take x. So we have to throw in a 0x up here. So 0x take negative x will be x, and we've got our plus 2. And so that means that the integral of x to the power of 5 plus 2 on x squared take 1 dx is equal to the integral of the quotient, which is x cubed plus x, and the remainder, which is x plus 2, over this x squared take 1 with respect to x. So now what we need to do is we need to consider our x plus 2 over x squared take 1 as x plus 2 over x plus 1 x take 1, as it's a difference of perfect squares. So we're looking at a over x plus 1 and b over x take 1, which means we can say that x plus 2 is equivalent to a lots of x take 1 when we get our common denominator, and b lots of x plus 1. So when x is equal to 1, we've got 3 is equal to 2b, and therefore b is equal to 3 on 2.
So when x is equal to negative 1, we've got negative 1 plus 2, which is 1, is equal to negative 2a and 0b. So a will be negative 1 on 2. So when we put this back in and we look at the integral, we have the integral of x to the power of 5 plus 2 on x squared take 1 dot dx is equal to the integral of x cubed plus x plus negative 1/2 over x plus 1 and 3 on 2 over x take 1, all with respect to x. Now when we sort this out, it becomes the integral of x cubed dot dx the integral of x dot dx, negative 1/2 of the integral of 1 on x plus 1 dot dx, and 3 on 2 lots of the integral of 1 on x take 1 dot dx. So each of those individual integrals, we have x to the power of 4 on 4, we have x squared on 2, negative 1/2 ln of x plus 1, and 3 on 2 ln of x take 1 plus c. We can take out a common factor of 1 on 4, so we have 1 on 4, and that leaves us with x to the power of 4 and 2x squared and negative 2 ln x plus 1 and 6 ln x take 1 plus c. We could then combine the natural logarithms, but I think this is simplified enough. So hopefully that process makes sense. This is quite a complex scenario where we have to first go through the polynomial division in order to get the quotient and the remainder. The remainder is what we use partial fractions with. And we still need to go through the process of calculating the value of the parameters a and b before we can find the integral. So last scenario, we're looking at finding the antiderivative of 4 over x plus 1, x squared plus 1. Now x squared plus 1 is a sum of squares, and hence it has no further factorization. So when we consider this 4 over x plus 1 and x squared plus 1, we're looking at it in the form a over x plus 1 as a linear denominator and bx plus c as we have a quadratic denominator. So we've got 4 is equal to a multiplied by x squared plus 1 and bx plus c multiplied by x plus 1. That gives us our common denominator of x plus 1, x squared plus 1. Now we don't have to write that in. Now when we let x equal negative 1, because that will cancel out this bracket here, let it equal 0, and therefore the whole term will be cancelled. We have 4 is equal to a lots of negative 1 squared, which is 1 plus 1, and that's 2. So 4 is equal to 2a, therefore a is equal to 2. For this scenario, the next step is we let x equal 0. So when x is equal to 0, we've got 4 is equal to 0 squared plus 1. So that's 1a. And 0b plus c. And 0 plus 1 is 1. So we've got 4 is equal to 1a plus 1c. A is equal to 2, so we've got 2 plus c. And therefore c is equal to 2. Now in order to find the value of b, we have to choose another value. So let's say let x equal 1. So now we've got 4 is equal to 1 squared plus 1, which is 2a. We've got one lot of b plus c, so b plus c, and we're multiplied by 1 plus 1, which is 2. So we've got 4 is equal to 2a plus 2b plus 2c. And when we put in a and c, we've got 4 is equal to 2 lots of a, which is 4. We don't know b yet. And 2 lots of c, which is 4. So we have 4 is equal to 8 plus 2b. Subtract 8, and we have 2b is equal to negative 4, and b is equal to negative 2. Now that we've got all of that, we can rewrite. So instead of looking at the integral of 4 over x plus 1, x squared plus 1, we can break that up, and now we've got the integral of a over x plus 1, which is 2 over x plus 1 dx, plus the integral of bx plus c, so that means we've got negative 2x plus 2 over x squared plus 1. And so we can break this into 2 integral 1 over x plus 1 dx. We've got subtract integral of 2x over x squared plus 1 dot dx, and then we have plus 2 integral of 1 on x squared plus 1 dx. So the first one is nice and simple. We've got 2 ln x plus 1. As 2x is the derivative of x squared plus 1, we've got negative ln x squared plus 1. And then we've got 2 lots of, hopefully you can recognize this one as an arctan. So think of it as a over x squared plus a squared integral of with respect to x, which will give us arctan of x on a plus c. So that means in this case a is 1, so we have 2 lots of arctan of x on 1, or just x, plus c. And there we have that integral. So this one again was quite complex. The last 2 were difficult questions. The previous questions were relatively straightforward once you get fluent in this process. Okay, so hopefully that helps. There's a few examples for you to practice with. Thank you for listening.